Well, thank you very much for the opportunity to speak here. I know SpEC and SpECTRE are a little bit orthogonal to most of the other codes that are the real reason for the workshop. So I'm going to tell you a little bit about SpEC and SpECTRE, mostly for vacuum, just to focus the talk. Let me start out with just a little bit of motivation. This is not new but just to set a starting point. Merging black holes, if you want to solve them on a computer, the starting point is they obey the equations of general relativity. And what makes those equations so difficult to solve is that they're nonlinear. And that means that a sum of the solutions is not necessarily a solution. So a good example of that is fluid dynamics. A single black hole is like a calm, think of that like a calm surface of a lake where maybe there's a little perturbations, but nothing too serious. And those solutions came, for the spherical case, the solution that turned out to be a spinning black hole came very quickly after the Einstein published his equations. But it took until 2005 to get the first binary black holes. Two black holes together don't just sit there, it's more than the sum of the parts. And that nonlinearity is why you have to do numerical relativity. And since then, there's been, since 2005, there's so many codes, and I'm sorry if I missed yours. I tried to give what's now mostly teleological shout outs to talks that people have given, and a couple that they will give on all the different things going on in numerical relativity. Like we've seen, numerical relativity is a very active field of research now. This is a table from this that you've seen before, and it doesn't even have all the codes that are on it. There's a new elliptica initial data code that's not even on here. All these codes, it's important to have multiple codes, like we heard in the discussion yesterday morning, so that you can check them and make sure that they agree and that they're getting the thing that's solved correctly. And another thing that you can do when you have a number of these codes is you can start focusing on creating the numerical relativity model waveforms that you need to tune analytic models to interpret gravitational wave observations. Now in this talk, I'm going to focus just on two codes, SpEC and SpECTRE, but this is just a piece of the broader landscape. It's just a piece that's a little bit different from most of the other codes that are on the list here. So I'm going to start out by talking about SpEC. SpEC is the spectral Einstein code, but it just goes by SpEC now. Originally developed by Larry Kidder, Harold Pfeiffer, and Mark Shield when they were all at Cornell. The story, the way I heard it, was they told Saul Tucholsky they wanted to try spectral methods, and he said, "Don't do it, they won't work." And then Saul was out of town on a trip, and they tried it in spherical symmetry while he was gone, and it worked. Then he came back, and they said they wanted, and then they had said something again about spectral methods. He said, "No, don't do it, it won't work." And then they're like, "Okay, check it out, it works." And then that was the origins of trying to do spectral methods. Now it's a closed source code primarily because as it was written, it wasn't documented properly, and the burden of supporting it is more than we can do. But the results from SpEC are public. We have a public catalog of waveforms. The URL is here, and I'll say a little more about how to make use of those waveforms if you want to compare them to your Einstein Toolkit waveforms or whatever waveforms from whatever code you want to use. I'll say more about that in a little bit. Here are a couple of highlight results. This is a little washed out in the bright lights, but maybe you can see, people on Zoom can't see me pointing. Maybe you can see how much this is showing what a binary black hole merger that we calculated would look like by solving the ray tracing problem to show what the light-like geodesics from the background stars would look like. And these dark regions are called the black hole shadows that have been made famous by the Event Horizon Telescope project, finding the shadows from like Sagittarius A star and M87. The gravity, so this is just one way to visualize the very strong curvature. Another way to visualize the curvature is shown down, let's stop this one. Whoops, that mouse isn't going to stop me. Okay. And let's go to the next one. This is going to show, it's going to zoom in In the inside there, the colors, the bright colors are the rate of flow of time, they're the laps. The arrows are the shift, how space is being dragged around. The two horizons are just shown up above because this bottom thing is sort of like an embedding diagram, but it's really just the spatial Ricci scalar because this embedding diagram problem isn't solvable as far as I know. But this is an approximation to give you a feel of what the curvature would look like. Now, as the black holes merge, it's going to go into slow motion. The two horizons get deformed into like a potato-shaped black hole. Then at the bottom, right where my zoom controls are hiding everything, is the gravitational waveform. But that also, I don't. All right. It's just risky when you're getting it. I don't know. It's a little bit washed out, but there's a waveform down there. I'll have brighter waveforms later. Trust me, it's okay. Yeah, you got to squint to see the blue. Sorry about that. All right. Now, let me give you a bit of history, a bit of a timeline. SpEC, so, I mean, I don't know exactly when this spherical symmetry story that I told you happened. I don't know what exact year that was. I'd have to ask. But the SpEC code started with the first commit into what was then CBS, the latest, greatest version control before we, but now it's all back ported into Git. And then it took 6 years to get the first inspiral. Now, going from inspiral to merger isn't necessarily, well, it's a lot more challenging in the methods that we use than in other codes. And I'll say why in a little bit later. So it actually took us another couple of years until 2009 before we were able to really do the full thing, including the merger and the ring down. But in the meanwhile, we had at the time, this was the longest and most accurate inspiral by far, and that was handy for doing the first really high accuracy comparisons to post-Newtonian waveforms, for instance. And then after the first simulations, then there's, as I'll say a little bit more later, there's lots of different merging black hole configurations you can have. So then we started building catalogs of waveforms, just like a lot of other codes that have gone through a similar life cycle. This is just the life cycle for SpEC, and that's where it is today. So it's still an actively developed code, but it's mostly occasionally you'll add a feature, but mostly for binary black holes, it's just maintenance. It's 20 years old. So it's sort of like where Microsoft Word on the Mac was in like 2004. So, maybe they'll change things up, but it's like the way it works isn't fundamentally going to change. Okay. So let me say a little bit about methods. So there's sort of two different families of methods for doing numerical relativity. Most codes like Einstein Toolkit and others on the left for initial data, well, there's different ways you can do it. There are spectral codes, but the initial data is a different problem. It's puncture data is what most codes use, but we use a kind of initial data that involves excision, where you actually remove inside the two black holes from your computational grid. There's usually some simplifying assumptions made so that you only have to solve one Laplace-like equation, but in SpEC, we solve a family of 5 equations. And that's just because we're using a different formulation of the initial data equations. Then once you have that initial data and you want to take time steps, then most codes use formulations like VSSN or CCZ4, but our code uses a different formulation, and I'll say more about it in the next couple slides, called generalized harmonic. And the numerical methods are also tend to be different. Most of these codes use high order finite differencing. And so the idea of high order finite differencing, I mean, you're all more expert on this than me, but just for the purposes of this talk, you can think of just laying down grid points and have values of all the functions you want to measure at each point. And then this isn't really what you do. Of course, you do a high order version of this, but you can take derivatives by comparing values at neighboring points. And because of the moving puncture trick, if you have a singularity, as long as it doesn't hit one of the grid points, you're fine, because it's just finite differencing. You can turn grid points off if you need to. That's like my spectral methods person's sort of cartoon understanding, and feel free to jump in if I say anything wrong about the finite differencing codes. On the spectral side, it's just different. We remove from our grid these holes. You can see these deformed shapes for the two black holes. The reason we have to do that is in spectral methods, you represent all the functions, not just as numbers at grid points, but as series expansions of some coefficients A, that you solve for times some known functions, the basis functions B that you know. And then that has some advantages. You can take derivatives analytically, but so you don't have communication between distant grid points for a wide stencil. But one disadvantage is because it's a power series, you can't just like turn a term off the way you turn a grid point off in finite differencing. So we have to do this kind of excision, and that makes our life harder in some ways. Now there's lots of codes that do what's going on the left, especially for this talk, the Einstein toolkit and the codes that derive from it. But SpEC is it's not the only spectral code for initial data. It's the only really widely used for producing binary black hole waveforms for gravitational wave observatories pseudospectral code. I guess that's enough qualifiers to be accurate. So let me tell you now, and there's advantages to both. There's a lot more open source frameworks. These finite differencing is more robust. There's a lot more of these simulations. Spectral simulations tend to be more accurate at lower cost. The errors converge exponentially with resolution instead of some power law with resolution. And these methods are also especially good if the black holes are spinning really fast for some technical reasons that I have a bonus slide for if you want to hear about later. All right, so let me tell you a little bit, because we use a different formulation than you might be used to. Let me say a little bit about where, I'm not going to derive it, but I want to give you a feel for what this generalized harmonic formulation is about. So the goal, like with all numerical relativity codes in vacuum, is to solve this equation, G mu nu is 0. That's the compact way to write it. But writing it in a way that the errors don't blow up exponentially is the whole trick. You're going to solve for the space-time metric. So the basic strategy, just to lay out some terminology, you have a slice of time that's your initial time, and it has some normal vector to it, and then you have some times a little bit later. And the idea is first you have to solve for that initial time. It's like the first frame in a movie. And then here's your constraint equations. Those are some components of the Einstein equations. And you can think of those, if you're not used to looking at the formulations in detail, you can think of those as just like if you were doing Maxwell's equations, the divergences are 0. So the field lines don't end. I don't know of a nice geometric interpretation. Maybe there is one for these other equations. They go by the names of the Hamiltonian and momentum constraint. And then the rest of the equations have time derivatives, and they say how things are going to change as you go forward in time. So what you have to do is, even though the constraint equations aren't involved in terms of the time derivatives, they still had better stay true. So the idea is once you have that initial slice, you step forward in time and then say, okay, now that's my initial slice, and I'll take another step a little bit forward in time, and you just repeat this a lot. Now, with that idea, how might you do this for something like the wave equation? So here's the wave equation with the velocity set to 1. This is something that you meet in your undergraduate physics classes. Now, if you were to solve this on a computer, this equation, there's lots of ways you can go, but one way you can go is to make the derivatives first order instead of second order. There's lots of literature about results that show existence of solutions and things like that if your system is a first order system. So you can just define some new variables. Pi is the time derivative of the wave amplitude g, and phi is the space derivative. Okay. Then you can plug those in to the original equation. And if you plug that definition of pi in up there, you get a time derivative equation for pi. The definition of pi gives you a time derivative for the metric, and then you can differentiate this phi thing at the bottom there. Now you've got a set of 3 equations for your 3 variables, g, pi, and phi. There's just one thing though. Those 3 equations are not the full system. You also have this thing called a constraint. Phi had better be equal to the spatial derivative of g. Okay. Now this is the kind of system that we evolved. This is the kind of system generalized harmonic is. And in fact, generalized harmonic looks a lot like this. Now let me show you the actual equations that we evolved on the next slide. So these are the evolution equations. And there's lots going on here, but just look at the first terms here. There's a time derivative of, instead of the wave, now put some tensor indices on it, and it's the metric. And pi is not exactly the time derivative of the metric, but it's kind of like it. And then phi actually is the spatial derivative, just like before. And then there's just lots messier right-hand sides because it's the nonlinear Einstein equations and they're messier and more complicated. At the same time, there's a whole bunch of constraint equations. Mostly we call them C, which stands for constraint. This one here is called F. I asked Mark Shield why they called it the F constraint, and he said, well, look at it. There's nothing more to it than that. Yeah, and I got to code that equation up in SpECTRE, and now I understand what he was talking about. That was fun. And here, look at this equation of this constraint with 3 tensor indices on it. If you take away that A and B index, this is exactly the same as that constraint from the wave equation. That's one of these equations that just has to stay true all the time. So that's just, oh, and also these equations, it's called generalized harmonic because it involves this function A here, and this is basically box of the coordinates. And so that's sort of where the harmonic part comes into all this. So that's just to give you a bit of a feel for it. And if you haven't seen generalized harmonic before. Could I comment on the gammas? Yes, thanks for reminding me about that in the chat. I was going to, and then I forgot and was all ready to go to the next slide. So you might notice there's these gammas here, and those gammas tend to be multiplied by the constraints, these C's. Now, why would you do that? These constraints are all supposed to be 0. So you haven't really changed the equation. You added 0 to it. But that's only true if they're exactly solved. If they're approximately solved, then, okay, you've kind of added 0, but you can add something that should be 0 with infinite resolution, but isn't 0 with finite resolution. And these terms are added, and those gammas are chosen to have the correct signs and values so that if you have some errors, like say your constraints are 10 to the minus 15 instead of 0, that those 10 to the minus 15s don't exponentially grow to become 1. So those gamma terms with all those C's in there, that's what that's about. Okay, so thanks very much in the chat for asking about that.
That's something you set once at the beginning, or are they dynamical? They have to change.
That's a good question. Do the gammas change during the evolution? No, we just set those once. That's it. You do change for different problems. Like for a binary, you would set them differently than for a single black hole. Oh, whoops, I do. And I don't know if there's another question in the chat because I should look.
I think it was on that.
Only that one. Okay. So by using these methods, which I've just tried to give you the feel for, this is what our catalog of waveforms looked like in 2013. It's 9 years later. That makes me feel old, but at least we've made progress. We now have 2,000, more than 2,000 waveforms, but I can't make a slide that shows you 2,000 waveforms in any sensible way. So we'll go with this. And what I want you to take away from this is maybe this is common knowledge at this kind of a workshop, but when you step back for a second and look, like all these waveforms really are very different. And there really is a need not just to solve this problem once, but to solve it for all the different configurations you have to worry about. All right, so that brings me to telling you something about I want to tell you about our catalog. And should you want to use it? Now, maybe you can just I don't know, check your phone and check your email or something if you don't ever want to use our catalog. But if you're curious about it, maybe you want to compare the waveforms from your code with ours and you'd like to know how it works. Well, the best way to use our catalog is actually Python. So there's a Python library called SXS. This was alluded to during the discussion yesterday. You can install it if you use Conda. Mike Boyle says Conda is the only way to go, so it supports Conda, but it also supports pip if you don't want to do Conda. I've actually switched back and forth a few times on whether I like Conda or not. But anyway, that's all you have to do to install it. Now, if you want to play around with this, I put on a GitHub gist of just a Jupyter notebook that has some of the examples I'm going to show you here. One thing you might want to do is pick a waveform from our catalog and actually get the data and maybe make a plot of it or use it or something. So how do you do that? Oh, before I get there, I want to warn you all, our waveform format is going to change pretty soon. We heard about this into a format that's more compact, so that's easier to download. But that means if you want to work with our waveforms, it's better to use Python because this interface won't change. It'll all be transparent than to try to download our files and write your own thing to read them because that kind of thing will break. We're going to post an archive paper soon talking about the new format. All right, so suppose you want to use this. Well, import NumPy and matplotlib so you can make some plots, and then our SXS library. So after you've done that, suppose you want to download a waveform from our catalog. So the first thing you would run after you import it is just sxs.load catalog. This line here will just get you your, this will download the latest metadata from our website. And so this will make sure you're up to date with whatever we have available at any given time. Then suppose you want a specific waveform. In this case, I picked waveform 305. This one, I mean, there's lots of ones you could choose. They're all given in our catalog an ID number, and then resolutions are called LEVs for some historical reason, but it really should be like res or resolution. And the higher the integer, the higher it is, but they don't correlate between simulations. So saying like it's level 6 in 305, higher or lower resolution than level 3 in simulation 200. That's like saying, you know, does it go up to 11? Right? They're not, you can't compare them now. You also can choose which extrapolation order to use depending on what you want to do with the waveform. And you can evaluate the waveform on this next line. Now I set all these to 0 for simplicity, but these arguments are the theta and phi positions on the sky. And I'm pretty sure it's that order, but I'll read the docs, but we'll confirm that if you actually want to try this. And then the polarization angle. And now you've got yourself the waveform evaluated somewhere. And that this has the raw waveform data before in terms of spherical harmonic modes. And then if you want to plot it, you can just plot waveform.time versus this evaluated waveform. Now, if you play along and try this, your plot might look a little uglier than this one. I didn't show all the matplotlib stuff you have to add to make the plot look decent. For some reason, every plotting thing that I know of by default makes crappy plots. I don't know why. They are all anyway. What's that?
Yeah.
Yeah.
Is this H plus or H cross?
That's a good question.
H.
Yeah, I think it's that is a good question. What's that?
Does it matter for just the purpose of the plot? And it's almost
It doesn't matter for the purpose of the
Yeah,
plot.
I'm
I'm
trying
looking
to
for
figure out how to-
straight head on.
I'm just trying to figure out how to use it.
Yeah.
Like, I want to get one.
I mean, it depends how you define your axis, right? If I
Yeah.
define my axis by 45 degrees turn, my H plus is your H plus.
Let me go on and
Please, yeah.
think about that. This function's just evaluates outputting one thing, but
Yeah.
let me come back to you about that one. All right. Now, another thing I want to make sure you know how to do if you want to play with the catalog is how can you know what's in there? So this is a little messy. Let me break this down for you. Catalog is something called table that knows about all the simulations. It's just a pandas table if you know pandas. But if you don't, basically in the square brackets and parentheses here, you could ask for instance, only the simulations whose mass ratio at some reference time after the initial burst of spurious radiation, that's what this reference means, is bigger than 1.2, say. We use mass ratio where it's the big one over the small one, so they're all bigger than 1. And maybe you also, to put an and here, also want the simulations that are spinning really fast with unequal masses. We don't have very many of them. This is the whole list. Then that's what you get. And then these last sets of things are just which columns you want to print out. Yeah.
So it's just reading here the metadata.
Yeah, this is just metadata, so you can figure out what we have.
And then the SXS.load, that there's an HTTP request that's happening.
Yeah, that just contacts our server in the background. Yeah.
It's only limited to page data because there's
No, you can get the BNS simulations that are on the catalog too this way. Yeah, I'm just showing a black hole example.
Am I wrong in remembering there's another catalog that analyzes the waveforms in a different way?
Another catalog.
I don't know if it's another.
Yeah, so we've got a small side catalog that has extra accurate data for the purposes of looking at like gravitational wave memory. And this isn't that. That's not part of our
It's
main
not
catalog.
linked in with this yet?
No.
Okay.
But you could, in principle, you just change like the
Yeah.
Or something.
Yeah, I mean, I'm not sure, there's some extra data that goes in there. And I think we need to sort out where we're gonna host it, because Zenodo got grumpy with us, but once we figure that out, they might be linked together, we'll see. Yeah. Yes,
Yeah, so I'm not familiar with polarization and spectrum.
Okay.
So how do we get local properties? Like, do you have like current horizon?
oh, that's a great question. Yeah, we have apparent horizon finders. They use a algorithm called fast flow. They'll start with a guess and iterate it until the expansion on the surface is 0, which is some tolerance. And then you can do surface integrals to compute quasi-local quantities, like the approximate Killing vector spin is how we measure the black hole spins. Other questions before I go on?
Is there any like methodology to how you're like which parameters you're generating? Like here, it seems like those are more so random.
Yeah, sometimes there is, sometimes there isn't. Sometimes we'll do a campaign of simulations. Sometimes we'll just say, oh, like some of these might have been inspired by some observation, although there's not really evidence for sure they were high spin. Maybe you wanted to make some high spin things to check. Some of these, like the ones where they're close to even numbers, like 1.499, like, okay, that's a lot of digits, but it started out as 1.5 and then it absorbed a bit of junk radiation at the beginning. And that's why the number is a little off. So some of them are just like, let's see if we can do a mass ratio of 1.5, which actually is pretty hard when the spin is 0.95. Okay, I'm going to go on and we can have, if there's time, I can answer more questions at the end. One last thing I want to show you is what's really easy. If you want to know what parameters we have, let me move this out of the way. You can just do matplotlib plot and just plot any parameters against each other like catalog.table. This is plotting the spin magnitude in dimensionless units, which we call pi. Black hole 1, which is the bigger one, which is black hole 2, which is the smaller one. And if you look at that, then you see most of our simulations have spins no bigger than 0.8 because that's the point where excision starts to get technically more challenging. So this is just to show you if you want to know what's available to try to compare, if you want to compare with your waveforms or something, this is what you can do. You can also access all our horizon quantities this way if you want to know like mass and spin versus time. I've got a bonus slide about that if anyone wants to see how to do that later. That's pretty much what I wanted to tell you about how to use the catalog. What I wanted to say now is a little bit about why this is hard. One reason is there's just lots of configurations you have to do. There's these 7 parameters, the dimensionless spins that are chi in our notation, and the mass ratio. Let's see here. Looks like I'm running low. And so here's our parameter space coverage. And I'm running a little low on time, so I'm going to skip ahead a little bit. And what I want to make sure I have time to talk about is, so far, what I've been showing is mostly focused on modeling gravitational waves for today's gravitational wave detectors. But of course, we have new detectors that are hopefully going to be running in the 2030s. Here's 3 of them: Cosmic Explorer, Einstein Telescope, and LISA. Now, all of these are going to be much, much more sensitive, and they will be able to achieve observations of signals with signal to noise ratios that are potentially on the order of 1,000. This plot down here shows you the range for binary black holes on the right and binary neutron stars on the left. So for binary black holes, 150914, the first observation, is very close to us. And the current detectors have a range that's getting out into the population. These new detectors will be able to reach so far away. Cosmic Explorer and Einstein Telescope would see all the binary black holes that there are. And that means that the ones that we're seeing today will be super loud. There's lots of things you could do with this. Just one example I'll call off this slide is you can ask questions about the nature of gravity. Is Einstein's gravity really right? If you're going to look for a small correction to general relativity, you need to be very precise in your waveform modeling to be sure that the deviations you're seeing aren't just systematic errors from your waveform modeling. So here's just this plot that I showed yesterday that says, just look at this column right here around the 2030s. If you have either Einstein Telescope or Cosmic Explorer, they will be able to see in combination with a network, something like 10 of these super loud signals per year, according to this trade study here. So these things
10
will
minutes.
happen. This is a plot I showed yesterday too that gives you a feel for what such a super loud signal might look like for a cosmic explorer. Now, how accurate your waveforms need to be depend on the mass on rho, which is the signal to noise ratio. Now, how accurate they need to be is an open question, but there's a sufficient condition. It might be a little too strict or a lot too strict, but this is a way that people estimate how accurate they need to be in terms of this is basically a dot product that's inversely weighted by the noise in your detector, this S here. And if you take that dot product, so the H's are the strain from the gravitational wave. And then the S is the detector noise. And then the mismatch is something you can define, which is 1 minus this dot product of a unit vector pointing in each direction, basically. So you make H1 into a unit vector, H2 into a unit vector using this dot product. And then if it's the same exact waveform, that will be 1. So 1 minus that will be 0. Okay. And then if you maximize over any potential offsets in time or in phase, then that's the mismatch. How good does it have to be? Well, this criteria says that it scales, that as good it has to be for the two waveforms to be indistinguishable scales is 1 over the signal to noise ratio squared. Here's how well that ratio does for our catalog, where we assume uniform noise. So it's not a real detector's noise curve, it's just flat, so that this is only showing differences because of the theory, not because of the noise curve. Now, if you plug in a signal to noise ratio of 24, that comes out here, and what you want for the waves to be indistinguishable, you want them to be on the left of that line. Most of them are, so that's good. Some of our oldest simulations, maybe not, but most of them do okay. But if you have the signal to noise ratio of 1,000, they're not accurate enough by this measure anyway. And this is just to motivate. Maybe we want to get more accuracy, and maybe the current codes could be tuned to do it, or maybe you want to think about using a new code. And the rest of the talk is going to be about the new codes that we're building, next generation numerical relativity code called SpECTRE. The idea is these kinds of arguments I just told you can be done more carefully and suggest that numerical relativity will need to be 10 times more accurate than it is so far. And also, there might be cases like binaries with very unequal masses that are prohibitive. Like Carlos is always doing these really extreme mass ratios at RIT, but you know, there's some high mass ratio regime where maybe it starts to get prohibitive, and that's something else that next generation codes could do if they can just scale to exascale machines. Now I highlighted here, well, SpECTRE's covered up there, a few codes that are using a couple different approaches. These are just a few examples of codes that are trying to use novel techniques. I'll say what some of those are in SpECTRE a little bit later. And there's other codes that are using the same kind of methods as usual, but just doing better parallel frameworks. Like we heard about some of those earlier today. Okay, so here's that timeline I showed you about SpEC. SpECTRE is much earlier in development. We started thinking about how it might work in 2012, but the first commit was really, where we started really writing the code was in 2017. And we got our first Inspiral working, not published yet, in 5 years later. So, you know, by the time we publish it, about the same pace as before, about 6 years from starting the code to getting everything together. It's, you know, you wish it went faster, but that's how it's going. And this can give you an idea about the time scale for getting the first complete simulations out, maybe in a year or two, and then catalogs after coming of SpECTRE waveforms after that. So how does SpECTRE work? Well, it's an open source code, unlike SpEC. It's a next generation code. One novel technique for numerical relativity that it uses is the discontinuous Galerkin method. I want to give you a feel for how that works. In a discontinuous Galerkin, you can divide up the space you want to model into a bunch of cells and expand everything in terms of series expansions of basis functions. I call it phi instead of b like on the earlier slide, but this is the same idea as spectral methods. Heuristically, I mean, there's some technical differences like the fluxes between the cells, but heuristically, spectral methods tend to use a few cells that are very big, like spherical shells, and DG tends to use lots of cells that are very small. DG has an advantage that the cells only need to talk to their immediate neighbors. say more about that in a second, but both basically DG is, they're sort of limiting cases of the same general idea, where DG has more cells that are with a smaller order in the series expansion, and spectral methods tend to
5
have
minutes.
a bigger N in that series.
5 minutes.
Fewer cells. Versus finite differencing, you can think of that as a limiting case where basically there's just one number at each point. Okay. Now, like I said before, these have trade-offs. Sorry, is there a question?
You gotta find it.
Yeah, I can see the clock even if nobody else can. So that's why I'm skipping ahead on some things. So don't worry. Okay, so let me just give, so both of these methods will converge exponentially if the solution is smooth as you increase this N here. And another big advantage is these methods, the DG method communicates locally, only with nearest neighbors. So it minimizes the communication costs. The second thing is task-based parallelism. And I've just got an analogy for you about this. Our old code, SpEC, just runs N copies of the code, 1 per core. And then if statements say which part of the grid it's going to work on. And it synchronizes a lot. And this is a lot like if you're on a Zoom call and you're waiting for someone to unmute and they don't know they're muted and everyone has to wait. It's annoying. Task-based parallelism is more like using Slack or texting. You know, something wants some data, you want some data, it asks for it, and then it just goes, the code will just go on and do other things until it gets called back and messaged back that, okay, now it's ready, then it can continue. So it's there's much less synchronization points. Okay, so what results do we have? So here's a simple little problem where you drop a gravitational wave on a single black hole, which you totally can't see, it's all washed out. But this is what the horizon's scalar curvature does. This is its shape. So it rings and then it rings up, then rings down. And I did a strong scaling test where I ran the same high resolution simulation on a bunch of different cores. It's not perfect, but you know, we got it's not terrible. It's something like about 90% up to 4,000 cores. Now we have our first binary black holes working. This is the first one that we managed to get working. It ran for a few orbits here. I've got some caveats and about how this works. There's some tricks that we use. So one thing you need when you remove excise part of the domain is you need to move your grid to follow the black holes as they move around. We use a control system similar to how like a thermostat would work to keep the grids moving, to hold the horizons centered there. What we don't yet do is deform the horizon's shapes and sizes like you would need to if you want to do a merger and a ring down. It's still in progress. The apparent horizon finder I mentioned before, we have a horizon finder that can follow the black holes as they move around. It's the same approach as SpEC, just ported over into this new parallelism infrastructure, which means in real life, this was the biggest pain in terms of getting it working and finding and fixing bugs of all the things. Because
2 minutes.
Anyway, and then these simulations I'm showing you now use adaptive local time stepping. So at different points, you can stably take bigger or smaller time steps depending on the resolution there, and the time stepper takes account for that. And so just got a couple more slides. Here's a longer one that was done very recently. This is current as of last week, and the colors are showing the rate of flow of time, just to give you a feel of how many orbits. Now, there's 2 black hole orbits, and they're not crossing each other, so it's really hard to see on here. But that gives you an idea that we used initial data where we knew it wasn't very eccentric. So this is sort of the limits of what we're able to do now. And one last thing I can show you is here's a movie I got today from one of my undergraduates at Cal State Fullerton working with me. And this is just to show you, yeah, it's all washed out. But up at the top, you see those little black dots? Those are the horizons. So we're starting to work on
1 minute, please conclude.
Visualizations of the curvature of the horizons. Now, should you want to play with,
Here it's much better.
yeah, should you want to play with SpECTRE, try it out. Go to spectrecode.org. If you use Docker, you can get a Docker container that simplifies installing all the dependencies. Unless you've got an Apple Silicon Mac like me, Docker stinks on there, so you probably want to. We've got instructions, or basically email me if you want to do it that way, or build on a cluster. And then the GitHub page.
30 seconds,
where we do
please
our
conclude.
continuous integrations. If you have any questions, feel free to file an issue. So I think I will leave it right there, and I'll be happy to answer any questions that I have time for.
Great. Well, let's thank you. Li Wei, okay, maybe not. Oh, yeah, Li Wei, can you unmute and ask your question?
Yeah, thank you. So I still have a question about
You have your hand raised. We can't hear you.
Yeah, probably because Geoffrey's muted.
Oh, let's switch back.
Oh, okay, sorry.
Now that it talks
I think I
slowly.
know what's, yeah, that's it. Thank you.
Let me, oh, here we go.
Hello. Can you hear me?
Sorry. Yeah, go ahead and ask. Go ahead and ask your question again.
So I still have a question about the gamma terms. So I noticed that the GH system on your slide has some difference with the old version of the GH system. So you have extra gamma 4 and gamma 5 terms, which are, if I remember correctly, it is trying to make the constraint of evolution system simpler. But I wonder, does it have any effect on the accuracy in the real run? Sorry, I cannot hear you.
So the question is, do gamma 4 and gamma 5 have an effect on real world accuracy? So the answer is yeah. I don't know about gamma 4 and gamma 5 specifically as compared to the others without doing some specific tests, but these constraint damping parameters are absolutely crucial for keeping the constraints from blowing up. That's one measure of error, is that those constraints that are supposed to be 0 are small. And setting those to the wrong value is a great way to get your simulation to blow up and crash right away. Other questions?
You've done already some simulations. Is it clear if you're gonna be able to meet the accuracy requirements for next generation detectors? Is this system?
Yeah, so the question is, will we be able to meet the accuracy requirement for next generation detectors? We have not yet done that assessment for SpEC or SpECTRE, but my group at Fullerton is starting to look into it. There's reason to be optimistic for SpECTRE because it has promising scaling and you can get more accuracy by brute force with more resolution. There's also reason to be encouraged because it has exponential convergence when the solution is smooth. But we don't actually, that's just encouragement. We don't have an answer yet. We'll have to look into it.
And also, next question, can you say, assuming, I know you have like scaling to some certain amount of cores.
Yeah.
Will you be able to also have enough points to fully, like, will it be feasible to fully sample the phase space?
That depends on the resolution. So will you be able to, how many cores you can go up to depends on how many cells you have. And if you refine and have more cells, like cut each cell in half each dimension, you have 8 times as many cells.
2 minutes.
It might be that you're going to need black hole only for like simulation with matter. Are you really going to gain, like in some test problems where we scaled up to 100,000 cores or something like that. But it scales pretty well for the single black hole up to thousands. A binary black hole has more cells. So that's, but it remains to be seen where that cutoff is.
Yeah, so my question is, the SpECTRE compared to SpEC introduces DG and oscillator.
Yes.
Do you have a sense of which one, if any of the two, is more important in achieving your goals in terms of scaling and accuracy?
Yeah, which is more important? Well, that's hard to say because DG is kind of important for test-based parallelism to really be feasible. For it to work well, you need your queues to be full of all these little chunks of work to do. And that works better when you have a lot more smaller cells than the SpECTRE methods tend to do well with fewer bigger cells. So I'm not sure they're fully independent of each other.
1 minute.
And we haven't really done some systematic, can we try to isolate those effects?
Yeah. Let's see. Any other questions in the room or in chat? I had a question for you, Geoffrey, and that is, so I really like this import SXS thing. That's really, really cool. I was wondering if, those really cool histograms that you showed, where it's like, okay, I want to know whether the waveform I downloaded from the SXS catalog
Seconds.
is the left of that line or to the right of that line. Referring to the.
Okay, so to do that, you need to have some code that does mismatches. That's not part of our SXS library right now.
Okay.
Mark Scheel has the code, and you can talk to him if you want to learn how to do it with the way.
I do. Thank you.